Oh, this becomes like duck soup. I mean, this is overkill, what I did here. It's being rigorous, but it's overkill because I look at the series, n squared over n to the fourth, and I remember what my teacher told me. What did my teacher tell me? It's the tail behavior that matters. And in the tail behavior, when I see that, I see this. That's what I see. That's not 1. It's similar. I'm going to leave that dummy indexes. I didn't put equal to because they're not. It's going to sum up to a different number, but all I care about, I don't care about the number. I just want to answer whether it converges or not. Make sense? Done. Yeah, I could go through all that, divide highest powers, and that'd be very fine and dandy and rigorous of you. And I hope you live forever. You're wasting your time. Better just wrap your head around the big picture. Can I erase this? One more example. This is a tricky series, and that's kind of classic example. Why do I say classic example? Because 1 over n ln of n is not quite like 1 over n squared. Ln of n, if we graph it, for positive n, it doesn't grow as fast as n. This would be n. If that was n right here, that'd be n, that'd be ln of n. Grows less. So you can't say it's like 1 over n squared. You can't say, oh, that's like n and that's n, so it's 1 over n squared. It's in between. Do you guys see what I mean? It's in between. It's not. In other words, this is bigger than 1 over n squared. Because the denominator is smaller, as you can see by comparing the graphs. Make sense? So that's a case where, okay, I can't use a p-series thing. Not really. It's not readily made for it. Although I could do expansion here, but that's a whole different story and a whole different chapter. So, integral test, perfect for this. And you don't want to start with 1 because what's ln of 1? What's ln of 1? 0. So you would see that with like 2 or something like that. Right? Nothing sacred about 1. We care about one question. Converges or not. Okay. So I'm going to look at the integral from 2 to infinity, dx over x ln of x, because that envelopes this expression, just like I showed you before in the graph. I'm being liberal here because I'm trying to stay focused on the big picture. You do have to check that the terms decrease. You can't have this wiggly stuff because weird things can happen. The classic integral test doesn't have any wiggly things. You need to make sure the terms decrease. So it's a monotonically decreasing envelope. Monotonically decreasing envelope that envelopes the series terms. Does that make sense, those words? Okay. And then you just got to do a u substitution here, which you can do. That's not a big deal. If I let u equal ln of x, then du is dx over x, right? So this is like an integral from alpha to beta of du over u, right? So this is just ln of u from alpha to beta, right? And if I don't want to figure out the new limits of integration, which I can easily do, I'll just go back to the old variable. Cause u is ln of x, right? You're done with the upper limit. That's not finite. Very interesting. Because you would think it should be, because, you know, it's reminiscent of n to the 1 plus epsilon, but no, this is ln, it grows very slowly. Not good enough. You know, n to the 1 over n to the 1 plus epsilon is like 1 over n, and then n to the epsilon. And that beats out the ln of n. It's like an in-between kind of scenario. So I said it's a classic example. And perfect use for the integral test. Okay.